Hello everyone. In a previous lecture, we have discussed about the design of the shafts, pulleys for bearing for them. Okay. So in this lecture, we will complete our remaining design. That is a design of idlers. That is a troughing idler as well as a return idler. Okay. Let's see how we can design a troughing idler. Okay. Everybody's visible screen is visible for everyone. Now the design of troughing idler. That for that we need a net load on each idler assembly. That considered as a W. W is equal to weight of conveyed material per meter into the number of spacings plus weight of the belt per meter into number of spacings plus the weight of troughing idler per assembly. So in that small in the numerical we can or you can say with the this can be concluded W is equal to GG plus GB plus GRO into the spacing between two idlers. As the density rho is equal to 1.2 ton per meter cube, the belt width is a 500 mm. The spacing between two idlers, that is a 1.5 mm, referring PhD page number 9.19. Let's see. Okay, the maximum space for idlers is given over here. We know the density is over here, and our table, that is a width of the belt over here. So the spacing is 1.5. Okay, so putting all the values, what we get, the net load on each idler assembly W is equal to 71.9 kg per idler assembly. And the standard design book, what do we get? We know that this 70% of total load from toughing idler. Okay, out of the 100% load, the central roller is takes 70% load, and the side idler will carry only 15% load on each side, so that the 100% load is distributed. For idler number 1, here it will take 15%, idler central idler will take 70%, and the side idler again, right side idler will take again 15%. So the 100% load will be carried. Now load carried by the central idler, because out of 3 the maximum load is carried by central idler. Okay, so we can only design that idler so that the in other segment we can put the same idler, so it can very easily withstand with the minor load. Okay, so the load carried by the central idler WC is equal to 0.7 into W. So WC is equal to 49.833 kgf, or you can say 498.33 Newton. Let the length of idler, that could be considered B plus the clearance of both sides plus the margin between idler divided by number of idlers. So in a troughing idler we are using 3 idlers. Value of B is considered, we have belt width, that is a 500 mm, the clearance on both sides, that is a 50 mm, and the margin between idlers considered as a 50 mm. So total value and the number of idlers which is seen over here, left hand side, central and right hand side. So 3 idlers we are considering in a troughing segment, so divided by 3. So L, length of each idler, is considered as a 200 mm. Chalo. Next, the design of central troughing idler. It is look, the diagram is look like similar to the pulley design. Okay, so the loads and uh, the shear force and bending diagram is as shown in figure, that is figure number 3.5. Okay, for axle load and for roller, the loads distribution is shown. Now the diameter is considered as a 25 mm. The idler diameter we consider as a 25 mm, which we have already described while selecting the belt design. So bearing selection, radial load which is considered as a 70.19 kgf, and the axle load which is totally neglected. We have already calculated the value of Fr. Okay, actual velocity, we know that the diameter of the pulley, either the outer diameter is 125. Okay, so based on this, the calculated speed is 199.16 rpm. Now actual, assuming the working life of the bearing, it is 3 years consideration. So for 3 years, the value of LH90, 3 into the 12 into the 30 into the 16. That 16 is nothing but the average working per hour, average working hours per day. 12 is the month, 30 is the days, and 16 is the hours per day. So LH19, so total working hours are 17,280 hours. So now convert hours into the million revolution, that is get converted by using formula L90 is equal to LH90 plus 60 into N divided by 10 raised to 6. So we get L90 is equal to 206.48 million revolutions. Now similarly, referring page number 4.2, P is equal to CR plus CR into X into FA, FR plus Y into FA into service factor. So as in a race is rotating, CR is equal to 1.1, X is equal to 1, Y is equal to 0, FR is equal to 711.9 Newton. By considering service factor with a no impact considering continuous impact load, service factor is equal to 1.4. Putting all the values, what we get, P is equal to 1096.36 Newton. Now here we are assuming the deep groove ball bearing. Referring page number 4.2, C is equal to L90 by L6 L10 raised to 1 by K into P. So putting all the values, what we get, C is equal to 6,479.83 Newton. So with respect to the DGBB, considering SKF 6005 with the value of C, static capacity and dynamic capacity are 7,800 Newton and 5,200 Newton. Okay, so dimension of the bearing is given over here, that is a bearing layout. Considering the length of hub is 15 mm. Now focus on this segment. We have designed this one. Okay, we have done the bearing design, shaft design. Now we have to design this hub diameter, then the outer diameter, fully outer diameter. Okay, so L is equal to 15. Considering the bending moment for the axle, L1 is equal to the width of the bearing divided by 2 plus thickness S plus TP. Okay, so considering a TS and TP is equal to 5 mm, so L1 is equal to 16 mm, L2 is equal to total length divided by minus twice of width of bearing. So total length is 200 minus 2 into 12 by 2. So the length L2 is equal to 188 mm. Maximum bending stress B max is equal to WC divided by 2 into L1. WC is equal to 498.3 divided by 2 into 16. So maximum bending moment is equal to 3,986.4 Newton mm. Now applying the bending equation, BM is equal to divided by I is equal to sigma B, that is design sigma B, into Y divided by Y. So applying after the applying the equation, what do we get? Sigma B is equal to 1.2987 Newton per mm. Now selecting the material for same, C is equal to C30 with sigma YT is equal to 300 and factor of safety is equal to 3. So design values, design stresses have calculated, and based on the design stresses, so design sigma B value is 100 Newton per mm square, and the induced sigma B is equal to 2.5987 Newton per mm square. So design stress is more than the induced, so our design is safe. Now considering the B BMD of for idler. So bending moment diagram for idler, that is referring from figure number 3.5. Maximum bending stress is equal to WC by 2 into LO divided by 2 minus WO divided by 2 into LO divided by 4. So equation what we get, WC into LO divided by 8. So maximum bending moment MB is equal to 12,457.5 Newton per mm square. So here the value of Z, or you can say similarly you can apply the bending moment equation. Before that you need to calculate the value of Z. Z is equal to pi by polar Z is equal to pi by 32 dO raised to 4 minus di raised to 4 divided by d0. Okay, so putting all the values, what you get, Z is equal to 54,380.96 mm square. Okay, and the induced bending stress sigma B divided by maximum bending stress divided by bending moment divided by Z, what we get, sigma B induced is 0.2297 Newton per mm square, which is very less. Okay, similarly here also we are considering idler from gray cast iron, that is a GC15. Sigma UT value is 130 Newton per mm square. Factor of safety is considered as a 5. So design bending stress is equal to 26 Newton per mm square, and induced was 0.22. So it is very less. Okay, so because of this our design is safe. As the induced stress is lesser than the design stress, our design is safe. Now similarly for return idler, the number of return idler are less as compared to the top run idler or troughing idler, because the application of return idler are only to give a support to the belt. So the belt while coming or after coming from uh, head end to tail end. Okay, so at that time it will not transfer any kind of material, so the number of idlers also very less over here. So we are designing for less load. Okay, process will be same as compared to the troughing. Okay, so you can refer diagram number 3.7 with the construction of a return idler and the loading diagrams for return idler. Now the preface speed is the same as that of the troughing and is equal to 109.6 rpm, and the net load on each return assembly, which is considered as a weight on the return idler assembly plus the weight per meter of the belt into the spacings. Okay, so by considering same, the number of spacings are here now get increased, that is a 3, previously it is 1.5. Okay, so WU is equal to 30.2 kgf. Now selection of the bearing by considering the diameter of axle will be same as the troughing. that is D is equal to 25 mm. The radial force is equal to WU, that is 30 Newton per 30.2 kgf or 302 Newton. The effective load or equivalent load, you can calculate P is equal to X CR into FR plus Y FA into service factor. Here the inner race is rotating value of CR, or you can say CR, or you can initially few cases we can denote it by V also. So that velocity ratio considered as a 1.1. FR is 302, X is equal to 1, Y is equal to 0, F is equal to 0, S is equal to 1.2. Okay, putting all the values, the equivalent load is equal to 398.64 Newton. Let the consider of life of the bearing of the troughing idler. That much life we are considering. L90 is equal to 204.43 million revolutions. Okay, so that much life we have considering. Now only because of the equivalent load the value of C get changed. Okay, so here the ball bearing is considers value of K is equal to 3. Okay, so calculated value of C is equal to 2300, sorry, 2348.34 Newton, or you can say 243.8 kgf. Okay, selecting a skep bearing catalog, bearing series of 60, bearing number 6005, having value of C is equal to 780 kgf. It is far more than that of the required. Referring page number 4.12. Now the design of axle for the return idler. Similarly, referring figure number 3.c, the bending moment diagram of axle. L1 is equal to WB divided by 2 plus TS plus TP by 2. WB is nothing but the bearing of bearing width. Okay, 12 by 2 plus 5 plus 5, L1 is equal to 16. Similarly, the length, total length here is 550 minus L twice into WB divided by 2. So L2 is equal to 538 mm. So maximum bending Bmax is equal to WU divided by 2 into L1. Okay, so the MB max is equal to calculated E is equal to 2460 Newton per mm. Now using the bending equation, B max divided by I is equal to sigma B divided by Y. Here sigma B is nothing but the induced stress, okay, induced bending moment, which we are going to calculate it. So similarly, or you can modify the equation, M divided by Z. Okay, so putting all the values, we can calculate the value of sigma B, that is 1.574 Newton per mm square. Similar material has been considered C30. Okay, so stresses we know that, and the design sigma B is 100 Newton per mm square and induced is 1.574. So when we compare these two stresses, what do we get? The design stress is very high as compared to the induced. So our design is safe. Now bending moment for idler assembly, the maximum bending moment that we calculated from previous segment also, that is WU divided by 2 into L by 2 minus W divided by 2 into L by 4. So it is WU into L divided by 4. So maximum bending moment which we calculated is 20,763.5 Newton mm. Now we have to calculate the diameter, or we have already diameters, that is D is equal to DO is equal to 225 and DI is equal to 115. Okay, so putting all the values, Z is equal to 54,380 Newton per mm cube. Now inducer sigma B is equal to MB max divided by Z. What do we get? MB designed or induced sigma B value is 0.3817 Newton per mm square. Now for troughing outer portion, we consider it is made up from grey cast iron, similar to that of Troughing Idler. The value of sigma B for this material is a sigma 3. Design value of sigma B is 26 Newton per mm, and the induced value is 0.3817 Newton per mm. So when we compare both, the design value is very much high and our design is safe. Now next one, the design of a reduction gearbox. If you have to design a reduction gearbox, so what should be the uh, transmission ratio for this, and how much number of stages we are going to consider? So that will be discussed in a nutshell. If you want to design it, you can continue the design of gearbox assembly. Okay, so the speed of motor is a 550 rpm, 1500 rpm, and the lowest speed, that is 39.5758 rpm. So the transmission ratio is input divided by output, so I is equal to 37.90. Now how we can consider the number of stages? uh, Number of stages is equal to square root. If we are going to considering the number of stages are 2, then it is I design is equal to square root of I. So 37.90 square root of 37.90, what do you get? The value of transmission ratio, design transmission ratio is equal to 6.15, but which is greater than 6, so it is not acceptable. So we have to go with the 3-stage. So I design transmission ratio is equal to cube root of I, that is 3.357, and which is lesser than 6, so it is acceptable. While design the transmission ratio, you have to consider 3-stage with the transmission ratio I is equal to 3.359. Okay, so in that way you can calculate the gear number of gears, as well as you can make a layout. In the last module of design of mechanical system, there is a one segment, design of 12 gearbox with its 3 stages. Okay, so in that you can also uh, you can easily understood what is the design gearbox layout, how can considering the speed ratio variation. Okay, so that could be you will understood in that part. Okay, so thank you very much. This is a first problem with respect to the design of conveyor belt. Uh, okay, so in the next lecture we will start with the fresh problem. Okay, so thank you very much. If you have any queries, you can feel free to ask me through WhatsApp, or you can directly make a call to me. Okay, thank you.